Hello, welcome to a problem session. So we are starting to do problems in, in the whole category of applications of gravity to planetary motion. We are going to do Kepler's laws later, and maybe satellites and spacecrafts. Okay. This is our warm-up. There are a couple of terms here that you might not have used before or you may not be clear on. So here is a orbit of Earth. It's a planar orbit. It's in a plane. And the angular momentum of Earth Sun system is perpendicular to this plane. Last time we had a polar coordinate in which we wrote down the equation of this orbit. Actually, we wrote down the equation of the particle mu, which is very close to mass m1. What are this m1? Our Sun is sitting at center of mass. So this is Cm, which is very close to where Sun is sitting. So if you go back, it comes from two-body problem, M2, M1, and we did the Cm, and this is R. And you can actually, if you go back, you'll see that we had this problem was converted into a mu problem based on M1, M2, and this R was written over there that way. And so we found, translating this into this coordinate system, X and Y. So this is one focus. Let's get focus 1, and another focus for ellipse will be that. And so at some time t, Earth will be there, which is very close to where the mu particle will be. So we're not going to distinguish it. This is R, and this is theta. So you can see from here, this is the furthest, and this would be on the other side, the closest point to the Sun. Sun is over here, and so this point happens. The closest point happens on January 3rd, and the furthest point happens on July 3rd. And the closest point is called Perihelion. Perihelion, and this is Aphelion. At this distance, Aphelion distance, and this is Perihelion. So that's what these two terms mean. So this orbit that we have written down, its equation in polar form, equation for this ellipse. So the energy was between this and this is negative energy, and that corresponded to epsilon 0 between 0 and 1, and this corresponded to ellipse. In this case, we had R equals to some R0, this is some constant, and 1 minus epsilon, this is the eccentricity, times cosine theta. And this theta, so this is at some time, unknown time, and this is at that time. So that's the relationship, and that's the orbit equation. So looking at this, you can see that when theta equal to 0, that's the furthest. So let's call it T Aphelion and T Perihelion. So T Aphelion is R0 1 minus cosine theta epsilon cosine theta at T Aphelion. In my coordinate system, the way this particular form of equation works out is this theta at T Aphelion is 0, and that's the form for the equation we have written, and that means cosine theta T of Aphelion equals to 1, and that makes it simply R0 over 1 minus epsilon. How about the perihelion? R of T perihelion, theta at T perihelion will be 180 degrees. It will be from here, this angle will be 180 degrees. So that makes it cosine theta perihelion will be minus 1. And this becomes R0 over 1 plus epsilon. So this is given and this is given, but I don't know what R0 is. But I really don't need to know R0 for epsilon, because I could take the ratio of these two, and that's what I'm going to do, and clean it up this. So taking the ratios, I get, you can see if you have this over that, so if I get the R at, let's call this R aphelion, and let's call this R perihelion. So I take a R aphelion over R perihelion. This is going to be more than 1. Then they have R0 over 1 minus epsilon, and you have R0 over 1 plus epsilon. And see, conveniently, I don't have to know R0. R0, if you know, R0 is actually related to angular momentum. So I have to find out L square over mu g m1 m2. So you really need to know that to get R0 directly, and we don't know that, so we don't need to actually know this. And from here you can just see this will flip 1 plus epsilon over 1 minus epsilon. And I want to solve for epsilon. You can see I can do one more thing, is if I add 1 to it and subtract 1 from it, 1 plus epsilon over 1 minus epsilon, and then if you took all these together, then epsilon will cancel out to one side, and then we'll have a 1 minus epsilon. I've got a 2 over there, and then I can bring that over there, and you'll have a 1 plus RA over RP, and the other side 2 over 1 minus epsilon. So this is RP plus RA over RP is 2 over 1 minus epsilon. And I think I can clean this up a little bit. We can just come out here and we can do 1 minus epsilon over 2 is RP plus RA over RP, and you can see this is inverted. Inverted is RP over RP plus RA. So this 2 goes on that side, and I bring epsilon this side, subtract. So epsilon equals 1 minus 2 RP over RP plus RA, and this looks like RA minus RP over RA plus RP. And I don't have to put all of this these numbers look really scary too, big numbers. So I don't need to actually use this guy. So I can put those numbers right here, or I can do something even simpler. Divide by RA everybody. So 1 minus RP over RA, 1 plus RP over RA. So I just need to figure that and plug in here. So what do we have? RP over RA. Clearly 10 to the power 6 will cancel out, and 147.1 over 152.1. And let me see what I did this calculation a little bit earlier. So when I plug this in, I get 0.0167. So that's pretty close to zero actually. It means it's quite circular. Now we have the eccentricity. Okay, so now that we have eccentricity already worked out, we can think about extending this problem. So what else can we find? You think something like energy of Earth. How about that? That will be a good thing to figure out how to solve that. And actually, surprisingly, you can do this here, and it's very illuminating. So we had the elliptical orbit, and along the major axis, the sun is here, and this is the Perihelion, and this was the Aphelion, and so together is 2 times A. A is the semi-major axis. So you can see that 2 times A is just RP plus RA, which is RP is R0 over 1 plus epsilon plus R0 over 1 minus epsilon, and you can just add these guys up and you get 2R0. It's pretty interesting, right? Now you already know this value. Now if you remember, the definition of epsilon was square root of 1 plus 2e L square over, I think, mu times alpha square, alpha over G m1 m2. This is sun and this is earth, and L was equal to mu so L was mu alpha. L square is actually mu alpha R0. So putting in here, I get a square root of 1 plus 2e R0 over alpha. So if I plug inside here, the square, and plug inside here, I get 2R0 over 1 minus 1 plus 2e R0 over alpha, and this one cancels this one, and then this R0 will cancel this, and this 2 will cancel that, and it's going to flip over. It's going to be minus alpha over E. So energy of the Earth-Sun system, just Earth, because we're doing the mu, remember, we're just doing the mu. Energy of the Earth is equal to this sum minus alpha divided by RP plus RA, and it's also less than 0 we want. And so what do we need? We need Newton's constant, mass of sun, mass of earth, and this rp plus ra. And these you can look it up. So pretty cool. You can find the energy of earth. How about angular momentum? Can we find that? Can you figure that out? Well, you can see that using this with that, I can figure out R0 and use this R0 and figure that. And what is mu? Mu is just coming from, mu is just M1, M2 over M1 plus M2. So I can figure out angular momentum as well. So I got angular momentum, I got energy, and actually you can do a lot more than this, but I think the video is getting long and I'm going to stop here. I will build up on a lot of these concepts throughout the week. I will talk to you later. Bye.